are linear. Right? That was brought up earlier when we were talking about unemployment rate, or we were talking about grades. If you study for 10 hours, your projected grade is like 126%. Right? This is assuming all linear, and in reality, there's a lot of things that are not linear. Right? And so we want to keep that in mind as we do this type of analysis. Right? And to test for some of these, we need to do a little bit more. We don't really have time to do that now. We also have to consider asking the question, I think Abby brought it up, about endogeneity or reverse causality. It's saying the same type thing, but in a slightly different way. What endogeneity or reverse causality is, it is possible that X affects Y and Y affects X. If that is the case, right, interpreting our variables can be a little bit misleading. Right? What we are saying here is, if this value of X increases, how does it affect this? Well, that can be misleading if we actually should have switched the variables. Or we can't say that with confidence. So we can't necessarily say causality in this scenario. Because does education affect income, or does income affect education? Right? And so it loses that interpretation, that ability, if we have problems with endogeneity. A lot of times for us, you might want to mention that this could be a case that I could make the argument that, well, maybe it's the other way around. Maybe incarceration rates actually affect the income, not income affect incarceration. So it's a problem that is always up in regression analysis. All right? So a couple of these key issues. All right, another one. Is multicollinearity. What multicollinearity is, and you will be asked to recognize these issues. Right? Multicollinearity occurs when two or more, so that's multicollinearity. Say it with me. Multicollinearity. Very good. Multicollinearity. This is when two or more independent variables are correlated with one another. Two or more independent variables, or x's, are correlated with one another. Excel can no longer then distinguish between that or the other. One of the famous examples is of multicollinearity is this. Alright, I want to determine the height of a person based on the size of their foot. Okay? So you can have the dependent variable being the height of the person and the size of my right foot. Okay? So the idea is, the bigger my right foot, the higher, the taller I actually am, right? So it's stuff, but this is a classic example of it. Right? So we have a very clear-cut relationship between the size of your shoe and that. Right. But now what if we include in our regression, again, dependent variable is height, and I have two independent variables now, the size of my left foot and the size of my right foot. Okay? Is the size of my left foot highly correlated with the size of my right foot? Yes. Alright, so now Excel has no idea what the heck is going on. Because you have these two independent variables that are highly correlated with one another. That means Excel can't tell the difference, and it makes them both insignificant. Right? There's tests, kind of a joking fashion. See, we're fun people, economists, right? There are tests that have shown this, right? If you just consider the size of one foot, that significantly explains your height. But if you put both feet in there, because of multicollinearity, neither one is significant. Because they're just wiping, canceling each other out. Right? And a lot of times you might see that in your analysis. How do we try and recognize that? The simplest way is to look at your correlation matrix. Right? your correlation matrix, we look at data, correlation. I did this before. You don't have to do it now, but just let me just show you what it is. So we have wind, a measure of offense and a measure of defense for all baseball teams. So our correlation matrix, ERA, or runs per game, is a measure of offense. ERA is a measure of pitching. These are how each of the variables are correlated with the amount of wins. This is the correlation between runs per game and the ERA. Okay. It's very, very little. There's no correlation between offense and defense in this problem. Right? Because it is very close to zero, I see no evidence of multicollinearity. As a general rule of thumb, this is not scientific or anything. If I see a correlation above 0.5, 0.6 positive, or below negative 0.5 or negative 0.6, then there's evidence that these independent variables may be correlated with one another and in a sense canceling each other out, which really biases our coefficients. Now there are more scientific ways to determine and statistically test if the model is suffering from multicollinearity, but I want you to be able to recognize it and define what that is. Okay, Abby, you had your hand up?
So the reverse causality, how would...
Does X affect Y or Y affect X?
Okay.
In advanced stats, we can show you how to take it. What we need to do is find an instrumental variable, which is correlated with one but not the other, but that's what it is in general. And that could be why you're getting results that you don't understand. You really believe that this should affect this, but then it's not coming up the way you want, then you step back and say, well, why is it? Is it my sample size? Is it suffering from multicollinearity? Is it perhaps reverse causality, this endogeneity problem?
What would reverse causality look? So you showed us how we would.
It's more of a. You wouldn't be able to identify it. There's not a test to identify it.
Oh.
What you would have to do is it's just more of an intuitive look at it, right? It's more of an intuitive type thing, right? And in economics, we just run into it. I say, well, I don't know if I can trust your results because of this. Consider adjusting it this way. But that is finding an instrumental variable that takes away from the endogeneity, which we're definitely not getting into now. That's advanced econometrics. But just recognize that it could be a shortcoming of these kind of models.
So we're looking at our data and like two of the things we think. I think it could have like some multicollinearity.
Yes.
Whatever. And I was wondering, would we write that on the paper, like say, oh well, we suspect this happening, and you know?
Yes. Wonderful, wonderful, wonderful question. All right. So you have three independent variables. This is what I want you to do if you really want to impress me, right? So you have your y is b0 plus b1 x1 plus b2 x2 plus b3 x3. So you have three independent variables, right? And you run them all together, just like this, with all of them in there, right? But then when you look at your correlation matrix, you notice that x1, or x2 and x3 seem to be highly correlated with one another. You see that because you looked at your correlation coefficient, it was like 0.9. Right? That's a problem. That's a problem. So what you would do is you would present the results that you have here. You would write, this is the results that we have, but we are worried about a possible issue of multicollinearity. Looking at the correlation coefficient, it's 0.92 between x2 and x3, which is very high correlation. What would I do? What would I do next if it is me? What I would do is run a regression taking one of them out. Right? What I would run the regression then doing y, just include the b1 x1 and the B2, X2. I would drop one of them, right? Because now you're really being able to focus and you're not having this other variable take one away. And then just to try and get a sense, I would also probably do a regression that has B1, X1 plus B3, X3 and take out the second one. Now, I would take out the one that is the least relevant or the least significant or the least correlated with your dependent variable. Or you can just pull out one and then do it, then pull out the other and do it again. As we keep doing it, we can do these pretty quickly, right? Data analysis, dependent, and choose our x's, right? But you do this, and you can identify and notice multicollinearity because of the high correlation between them, and then I would just pull one of them out. This is better than that if these suffer from multicollinearity. Now, we do, and I didn't have a lot of time to go into these details here, but we also made assumptions on our residuals. Underlying all of this, and this will be how I kind of close this idea of regression, is we did make some assumptions about our residuals. And more tests can show about residuals are what? Residuals are what is the difference between what we predicted, our y-hat, and the actual value. Right? That's the residual, that's what's left over. In order for these models to work and be reliable, we need our residuals to show no pattern over time. Basically, we want our residuals for very low values to be the same as the residuals at very high values. What basically that is saying is we are equally wrong throughout everything. Okay? It's okay because we're not going to have a perfect model. And we're trying to find this whole picture that best fits all the data in. But we don't want to be super right here, but then super wrong over here. We want to have constant, consistent residuals. That is the assumption that makes this work. If they display a pattern, or if they are dependent, that means they change over time. Showing a pattern, changing over time. This is the fun word, this is called heteroscedasticity. Right? The opposite of that is homoscedasticity, which means homo means they stay the same. It means uniform. That means our residuals show no patterns. When they show a pattern, that's called heteroscedasticity. It's easier to say that as opposed to the other. Right? And that is a fun word to try and spell. Right? If you want to go ahead and try and spell it, that's fun. Right. Anyone want to give it a try? Heteroscedasticity? Right. So this means restricted assumptions, residuals need to show no pattern. Otherwise, we run into problems. There are ways to diagnose this, but we're not going to be able to do that. But I want you to recognize some drawbacks that we have here. To spell heteroscedasticity, Heteroscedasticity.
Yeah, extra credit for that?
Yeah, sure.
All right.
But heteroscedasticity, hetero means it's changing, it's different over time. Okay? So some things to keep your eye out when we do regression analysis. All right. I know it's a lot. How you guys feel? Again, we have 3 hours again on Thursday, about an hour of which is going to be the groups and discussion. And so we'll have 2 hours to do some more practices with this. Again, wanting to throw things at you quickly so that we can see it. Oh, what I had before, yes. So I am going to take what you're going to have again for your final is I'm going to have another sheet. I'm going to take this and extend this to include chapters 14, 15, and 16. And then you'll have all the equations. So again, for the final, you'll be able to have this in front of you if you would like. But I'll add the new chapters for it. Right? Is that kind of what you mean? And we'll practice for 2 hours on Thursday too.
Yeah, but are you gonna be using all of that for the final?
Yes, it's cumulative.
I know, but it's gonna be the same.
Yes, I'm not changing anything here. I'm just going to add the other 3 chapters.
I would think you could take some out, but.
No, it's cumulative. It's everything. Alright. So how much do we get? Alright, so it's about 15 minutes. Let me introduce this. This last part, last topic. Alright, any other questions that we have?